Great, thanks. Thanks everybody for being here and for being on time after your coffee break. I'm here today to present a research agenda for data physicalization, which is an emerging area of research between the realms of information visualization and tangible user interfaces. So let's dive right in. So similar to the way in which the term visualization is used, data physicalization can refer both to a research area, which examines how computer-supported physical representations of data support cognition, communication, learning, problem-solving, and decision-making. At the same time, physicalization is also a physical artifact whose geometry or material properties encode data. Okay, that's very theoretical, so let me show you some examples to illustrate what that means. So you likely heard of Hans Rosling before. He's a Swedish professor of global health and an edutainer. And he's best known for his TED Talk, in which he educated people about global health issues using the Gapminder software. And about 5 years ago, he came on the TED stage bringing boxes, like this one here, and explained that each of these boxes will represent 1 billion people on the world. And then he explains how in 1960 only 1 billion people, the 1 billion most rich people, could afford driving. They are represented here by the blue box, while the rest of the world was only walking. And then he illustrated how that started to change and will continue to change while he added boxes and moved them around. So since then, he continued to use a variety of everyday physical objects in many of his talks to represent data. Of course, not all physicalizations require that someone animates them manually. So this here is an example of a set of physical charts, which you will be able to see in the interactivity section. I highly recommend checking them out. Okay, so physical data representations are not exactly new. The Mesopotamians already used clay tokens to deal with data. This was about 7,000 years ago, or even more. We don't know exactly, since this was before the invention of writing. And the Inca also used quipus to record and represent numerical information by knotting differently colored strings. Okay, so why should we physicalize data nowadays when we can just visualize them on the screen? And I asked Hans Rosling why he does it, and he answered me that they allow him to reach the mind of a large part of the public, because that's just how you represent data in everyday life. And many artists and designers agree with him, as the many so-called data sculptures in museums and art galleries from the last 20 years illustrate. So this year's Sky program also contains some projects which involve physical representations to engage people with data. And, well, all of them have already been presented earlier today. So if you missed them, it's unfortunately too late. But what they show is that one possible answer to this question that they posed, why physicalize, is to engage people with data. And there are some other reasons. So if we look back a bit, we find that physical models were also created as tools in education to explain complex processes to students, and by researchers to help them think and understand the data by manipulating it with their hands. And some famous examples exist, such as Nobel Prize laureates Watson and Crick, who built a model of the DNA, or Max Perutz, who studied the hemoglobin molecule. And also today, molecular biologists use now digital fabrication techniques to here create, for example, a DNA model. Okay, so thinking through manipulation is another reason why one might want to physicalize. So now you could wonder, why should that be? And one possible reason is that physicalizations have intrinsic support for active perception. So we know that action plays an important role in perception, and it's even so much so that it determines what you perceive and how that differs from what your neighbor perceives. So for example, if we take eye movements, then here on the left we can see the traces of a layperson, and he's focusing mostly on the face. Whereas an artist, which you can see on the right, takes in much more of the image and gets a probably quite different impression of this image. Similarly here, the woman who's moving her head closer gets a better impression of the details and the depth of these networks than the woman who's just standing in the back. If you visit one of the palaces here in Seoul, then the only way to get the full impression of the building is through locomotion by moving around. Or if you rather want to read a book, then you have to pick it up and turn pages. Otherwise, you will only get a very limited impression of the content of the book. So all these actions enrich our perception of the world, and they are built-in interactions with physical representations. So for example, these two people here, they are exploring an age pyramid of data, and they can move their eyes, their heads, or their entire body to change their viewpoint and take a closer look. Of course, with computers, you can also perceive actively, but interactions here need to be explicitly designed, implemented, and learned. Okay, so I mentioned only a few potential benefits here. As always, you find more details in the paper. I would just like to add that we're not claiming that these are unique to physicalizations, just that there's evidence available that so far justifies and encourages more research in this area. And so moving on to the challenges, and I will just highlight a few here. Let's start with how to design physicalizations. So for non-physical visualizations, we have a somewhat decent idea how to encode data effectively. And there's been a lot of work on when and how to encode data, using, for example, position, length, or combination of those. And such parameters are called visual variables. There are quite a few of those. And with physicalizations, our variables are not just visual, but physical, since we're not using pixels, but atoms to encode data. And physical materials have properties such as flexibility, weight, friction, or temperature, which cannot be perceived purely visually, and have thus so far been of little interest to the Infobis community. And we don't know yet which of these are useful to encode data and how they could influence the effectiveness of a physicalization. So for the common ones, between visualization and physicalizations, we can make some assumptions based on what we know for visual variables, such as that position is more accurately perceived than angles or length. But even these will need to be studied since we are in 3D space now. So a closely related challenge is how can we render these physical variables? So for some, like color, there are already some solutions. Here, full color 3D printing. Similarly, we already have a choice of different materials and can print flexible materials, can mix different materials in one artifact. And there's a lot of more research going on to further advance the possibilities in the area. But unfortunately, currently only very few research labs have access to the latest technology. And in general, the number of materials and especially control over their specific properties is still limited. Also, 3D printing is only just now getting from overnight slow to coffee break slow. And yeah, rendering smell or taste is, let's say, difficult for now. But those are our current limitations, and I guess they will be solved at some point. Others, like the laws of physics, are a bit more difficult to overcome. So on screen, we can easily create visualizations such as 3D scatter plots. But in the physical world, we cannot easily have free-floating parts. So luckily, some researchers already started working on floating things. And this brings me to the next set of challenges, how to support animation and interactivity. So physical objects always have some built-in physical interactions. You can look at them from different sides, or depending on scale, you can pick them up or walk around in them. Furthermore, with modular designs, you can take them apart, sort, or filter them. With this MRI model, you can create different views to look at different cuts of the data. But not all interactions can be implemented in a physical design, and for example, physical sorting is slow and repetitive. And for this type of task, we rather want to benefit from computation. So to distinguish interactions which include some form of computation from physical interactions, we introduce the term synthetic interaction. And these are different from physical interactions because they require some sensing to inform the system of the user's action and actuation to reflect the outcome of the computation. So for now, let's ignore the sensing and just look at the actuation part, since not all self-actuated physicalizations require sensing. So for example, the dangling string, which was discussed by Mark Weiser in 1995, simply consisted of a string attached to a motor. And the amount of the wriggling of the string indicated in real time how much network traffic was going on at the time at Xerox PARC. Or again, MSR's physical charts. There's currently no direct interaction, but still dynamic data is being displayed. And the same is true for these floating ping pong balls, which are part of the Hive Big Data think tank. So these are fixed types of physicalizations, and they are showing very specific types, bar charts or pie charts. And shape displays, which are more flexible, and they can be programmed to display different types of data representations. With these here, the variety of shapes is still somewhat limited. So for example, here you can only display 2.5D representations. But the HCI community has already been looking into shape-changing interfaces over the last years, and design spaces can help to explore new types of physicalizations. So the current limitations are the so far limited and fixed resolution of the actuated pixels or atoms, and the possible forms they can take. Also, shape displays are currently not exactly widely available, and so far don't actuate colors or textures. So we will hopefully get these at some point once programmable matter is available, and there it should be possible to manipulate material properties on a nanoscale level. So unfortunately, we are not there yet, and so we need workaround, and all of these will always sacrifice some properties to improve over others. So for example, a way to address dynamic color and annotations are hybrid setups, where shape displays are augmented with spatially mapped projections. Or a way to address the limited resolution is to instead use fabricated shapes, which bring the resolution up to the resolution of the used fabrication machine. However, here they sacrifice shape actuation for resolution. Over the last few days, I saw some exciting enabling technologies, and I believe that the boundaries will soon be pushed further on this. So as I said earlier, synthetic interactions use a combination of sensing, computation, and actuation. And to understand what the challenges are, let's look at a few synthetic interactions. So the tangible cityscape system combines a physical detail view with a larger on-screen view, here controlled through mid-air gestures, and it can show different data representations, which here are controlled through a touch panel. Then just after my talk, you will see an exploration of different interactions with the emerge display. Here are details on demand, controlled by touch, or removing data points, hereby directly interacting with physical bars. So to summarize, on one hand, we have physical interactions, which are directly built in the physical design and can make optimal use of human motor capabilities, but they're potentially tedious and slow. On the other hand, we have synthetic interactions, which can be powerful and convenient, but need to be explicitly discovered and learned. For now, it's an open challenge how to make optimal use of the two together. So now, to inform all the questions and challenges I discussed so far, we will need to collect empirical evidence. An important challenge is to get a better understanding of the actual benefits of physicality. So I often hear the argument that the system is better because it's more physical. But so far, we don't really know what that means. And to find out and base design decisions on evidence, we will need to compare to many other modalities. Also, importantly, we likely want to go beyond time and error metrics to study in how far physicality can affect depth of insights, level of engagement, or the memorability of data, which is something that Simon will be talking about later. So to wrap up, I talked about possible benefits, such as intrinsic support for active perception and the potential to engage people with data. Talked about some challenges, some design-related, such as how to choose effective encodings or how to design and support both physical and synthetic interactions. And I talked about challenges related to implementation, such as how to render physical variables or how to go beyond the current limitations of shape displays. And finally, how to evaluate what works, and most importantly, why. So let me conclude by emphasizing that with this article, we are trying to start a discussion on what physical data could or should look like with everybody who's interested. And so for that purpose, we created an online wiki where everybody who is working in this area can contribute and is invited to do so. Please contact us. Currently, you can find on the page a list of people across different communities involved, a bibliography of published articles, and a list of relevant emergent technologies. It's a wiki, so it's a work in progress. If your work is missing there, sorry, please let us know. And I would be happy if you participate. So thank you very much for your attention.
We have time for a few questions, so please come to the mic, state your name and affiliation, and ask questions. One thing I forgot to mention is don't forget to vote for the presentation you like. Let me ask you one question. So, in your paper, you mentioned the education as an application example, and I can kind of see how you could use physicalization for teaching basic concepts, etc. But for me, it's hard to envision how to use this data physicalization for actually analyzing real-world large data set. Do you have any comment about it?
Well, large data, I have not tried that so far myself. So far, physicalizations were mostly about rather small data. But I don't know. I don't know.
So my question is, do you see it as the limitation of the current technology, or it could be the limitation of the physicalization itself? What's your thought?
I would say currently it's mostly a problem with technology and scaling. And if you have a fixed resolution of a display and you cannot increase, I mean, that's one of the main differences, right? Between a screen, you can always zoom in further and you can have zoomable UIs. And currently, we're not able to do that with physicalizations. But you can go in scale, you can up in scale, and you can add on. You can, for education, I think you could, especially the aspect of the manipulability, I think that's something that could be very useful in education. And so far, we don't know that much. We have this anecdotal evidence that I mentioned, and there's a lot more in the paper. And I think it's definitely worth looking at.
Hi, Steve Harrose, Northwestern University. Really interesting stuff. I know you've looked before at measuring, sort of accuracy with touch versus when looking at things. I'm wondering, especially in those like dynamic displays that you showed where they're moving and stuff like that, where you might maybe not have the ability to touch it just because of the fragility of the moving parts. What do you think might be the a potential benefit in a physical display that animates?
That's interesting. Yeah. Thanks for the question. That's interesting. I think that Faisal will be able to tell you a lot more about that since he actually did a study with this display. That's Faisal. So you should definitely stay. From what I know, from what they observed is that people still try it. They still want to touch even when it moves. And it's an interesting tension, I would say, between stuff that animates and that might scare you away because it does things that you don't anticipate. But I think there's still the people still want to touch it.
Okay, cool. Thanks.